Last time we talked about the ideal gas law. What is the formula, the very basic formula for ideal gas law, Chris?
Pressure times volume is equal to N per T.
Yeah, PV equals nRT. So pressure, volume has to be in what unit? Liters. Is equal to moles times R, the universal gas constant, times T for temperature, and the temperature has to have what unit? Kelvin. And you know from last time that you select your R based on the units of what? Pressure. You've got it. So PV equals nRT, and hopefully you feel confident now working through those types of problems. And if you haven't done your classwork through number 10, this is going to build very quickly now. We did a lot of problems together. Most of you felt pretty good about it, but it's going to get worse and worse. Make sure you get periodic tables and calculators for everyone who needs it. You're the designated runner right now.
All right, who needs a periodic table? 1, 2, 3, 4, 5,
You're not going to remember all of those. Everyone's going to have to keep a hand up.
No.
I believe in
And for those of you who don't know, the calculators are in the clear plastic thing in the second drawer, all right? Because the other day somebody put them in the wrong drawer. I'm like, oh my gosh, where are my calculators? And I know you wouldn't
Who
steal
needs a
them.
calculator?
All right, now that we've got that straight, we are going to link stoichiometry to two different gas laws today. So this is going to review your stoichiometry chapter. Stoichiometry is very much a building block for many, many aspects of chemistry that we talk about this year. Most of you have extremely strong stoichiometry skills, which is going to help. Some of you need to strengthen those skills. We're going to link first stoichiometry to the ideal gas law. Ideal gas law is PV equals nRT. The first thing that you want to be extremely careful with your gas laws. Gas laws are for gases only. You only use gas laws if the state of matter is a gas. Don't put information about a solid or a liquid into an ideal gas law because you will crash and burn. Be very, very careful there. So the first thing you always want to be careful of is that you're only putting information about gases into the ideal gas law. Yes, you can go to the bathroom. Here you go. When you gotta go, you gotta go. The first thing you're looking at here is the equation must include at least one gas, otherwise the ideal gas law cannot be used. For example, in the first equation you have calcium carbonate reacting with hydrochloric acid to generate carbon dioxide, water, and calcium chloride. So you have at least two gases there, carbon dioxide and water. And you ran a reaction very similar to that one in your stoichiometry lab. In fact, it's shown here, where you had sodium bicarbonate, which is baking soda, that's what you used. You reacted it with hydrochloric acid to generate carbon dioxide, water, and sodium chloride. And the CO2 in the water went up into environment Neverland. So these equations are going to work in regard to ideal gas law and stoichiometry because you have at least one gas in those equations. You can use information about the volume of a gas to calculate the mass or moles of another substance. And when you're talking about mass or moles of that other substance, you're really talking about a solid or a liquid because you can get moles of a gas from PV equals nRT, and you can find mass or moles of a substance, or you can be given mass or moles of a solid or a liquid. You can figure out how many moles of the gas would either react with it or be generated from it, and then using your ideal gas law, you can determine a different variable about the gas, typically volume, although you could do pressure as well. You're probably not changing the temperature during the reaction because that might affect other variables. So in the first example, what we're looking at here, we want to know the volume of carbon dioxide. That's what we're looking for. We have 52.5 grams of calcium carbonate. That is a solid. You're going to react it with an excess of hydrochloric acid, so calcium carbonate will be your limiting reagent. It will be used up entirely, and it predicts or determines how much product you can generate. The pressure at which the carbon dioxide forms is 101 kPa, and the temperature is 25 degrees Celsius. Here is your balanced equation. I'm going to work this problem exactly as I would any other problem. I'm going to pull out the pertinent information first. That'll give me an indication of how to work the problem, what's going to drive it. Okay, so what I've got here, I want to know the volume of CO2, the mass of calcium carbonate is 52.5 grams, and calcium carbonate's a solid. So I'm not going to put information about a solid into a gas law. Gas laws are for gases only. The pressure is 101 kPa, and the temperature is 25 degrees Celsius, but we know better than to play in degrees Celsius. We've got to be in Kelvin. At first glance, this looks like an ideal gas law problem. I have P, I have T, I have the mass of a substance, I want the volume. But again, you do not put information about a solid or a liquid into an ideal gas law. So when you're given the mass of a solid and you want to know the volume of a gas, in step 1, you're going to do stoichiometry. And that will allow you to convert, in this case, the mass of a solid to moles of the gas in question. You have 52.5 grams of calcium carbonate, and you want to get 2 moles of the gas in question, and the gas in question is carbon dioxide. You're given mass, you want moles of another substance. You have already illustrated mastery of this concept from quizzes and tests. 1 mole of calcium carbonate is equal to its mass in grams from the periodic table. Calcium is 40.08, carbon is 12.011. You have 3 oxygen at 15.999. and that's going to be 100.088. Here's where the stoichiometric coefficients come in from the balanced chemical equation, which may or may not be provided. You may have to write one yourself. This one was given. You have 1 mole of calcium carbonate to 1 mole of carbon dioxide. And so that's going to be 0.525 moles of carbon dioxide. That is my N that will feed into the ideal gas law. Now, in step 2, you can use the ideal gas law, and this will allow you to calculate the volume of the gas in question, which is carbon dioxide. So you know that PV is equal to nRT. I want to know the volume of carbon dioxide, so I will divide both sides by the pressure. You've got 0.525 moles of carbon dioxide, a gas. We'll get to R in a sec. The temperature is 298.15 Kelvin. The pressure is 101 kPa. So what R constant should we use? The one with kPa in it, good, is 8.314 liters kPa over mole Kelvin. And we went over where that unit comes from yesterday.
Will the 3 conversions be provided?
They are in the back of your periodic table, and you're good to go there. kPa cancels, mole cancels, Kelvin cancels. You're left in a unit of volume, which you're left with a unit of volume which is consistent with what you want. And you've got a volume equal to 12.9 liters. We were given 3 sig figs, that's what we're giving back. So this is one way that you can link stoichiometry to the ideal gas law. Again, you'll either be given the mass of a solid or a liquid and asked for some variable associated with the gas, typically volume or pressure. Alternatively, you could be given all the information about the gas and asked for the mass of the solid or the liquid, and that's what the next one's going to show. So we're going to process the next one very similarly, except we're basically going to do the steps in the reverse order. Questions on the first? The second example says, what mass of sodium would be consumed? That's what we're solving for. We have 10 liters of hydrogen gas at 10 degrees Celsius and 96 kPa. You're not going to alter the temperature or pressure throughout the experiment. The equation is given here as well. And in your classwork, which you'll be able to complete, I gave you a lot of these problems. You need to be comfortable with this aspect of it. You'll see one of the pieces that we've done today on the quiz, but you'll see both of them on the test. So in this second problem, and again, I'm really going to break it down in the same regard because I want to make sure that you know how to approach it. So what I've got here is I want to know the mass of sodium. The volume of hydrogen gas is 10 liters. The temperature is 283.15 Kelvin. We don't plan degrees Celsius in this chapter. And the pressure is 96 kPa. And they gave us the balanced equation as well. 2 sodium react with 2 water molecules, solid and liquid respectively, to generate 2 sodium hydroxide, which is aqueous. It's water soluble. You'll learn about that in the next chapter. And our hydrogen gas. So this information is all about hydrogen gas. Now this time we're going to run it all backwards. In step 1, we're going to use the ideal gas law to calculate the moles of the hydrogen gas. So we have PV is equal to nRT. What would N be equal to if you manipulate the variables? Good. PV over RT. You've got to be comfortable with variable manipulation. Most of you are. Pressure, volume, R, same R because we've got kPa. And some of you too are having calculator issues. Remember, when you have more than one variable in the denominator, you need to bracket it off. You don't need any of the blue parentheses, but you do need the ones in pink. And I've got 0.408 moles of hydrogen gas. So that's the first step. And again, if you did your ideal gas law problems, you shouldn't have any issues solving for moles of a substance. Questions at this point? So now, if you want to get the mass of sodium, what are you going to do? You're going to need a mole ratio and then a mole to mass. So you're going to use stoichiometry to calculate the mass of, in this case, sodium. So from the moles of the gas, Michael, what would be my next step?
You would, the amount of moles in the equation for hydrogen gas on the bottom.
You got it. So you're going to have 1 mole of hydrogen gas, and on top will be?
Mole of sodium.
And Josh, what's the last thing you're going to do to get the mass of the sodium? You got it. So here's your mole to mass conversion. So cancel, 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 cancel. And you have 0.408 times 2 times 22.99. And that's 18.8 grams of sodium. Okay? So now, hopefully, you have some insight in regard to using the ideal gas law with stoichiometry. You have to understand when to use it. If you're given the mass of a solid or a liquid and asked about a gas variable, you'll need both. If you're given all the information about a gas and asked for the mass of a solid or a liquid, then you're going to need the stoichiometry as well. So that links stoichiometry to the ideal gas law, and you'll find several problems in classwork 3.2b. Now we can link stoichiometry to other gas laws. And this one I think is a little bit trickier. We're going to link stoichiometry with the combined gas law. The combined gas law is P1V1 over T1 equals P2V2 over T2. The key with the combined gas law that some of you may not recognize just yet is that when you use the combined gas law, you must compare the same gas under different conditions. So you can look, for example, at helium at one volume, temperature, and pressure, and you can look at what happens to its volume when you change the pressure and temperature. But you must be dealing with the same gas with the combined gas law. And if you can recognize that, you'll know when to use this gas law. None of the gas laws are tricky. It's knowing what to use when. So you can use the combined gas law when you have the same gas. You can't change it. The same gas under different conditions. However, if you want to compare two different gases under the same set of conditions, you're going to do a volume ratio as we talked about the other day. We had said that you can get volume ratios the same way you get mole ratios from the balanced equation, but it only works for gases. For example, it says in step 1 you're going to use volume ratios to calculate the volume of a gas under the first set of conditions, then the combined gas law to calculate volume or pressure or temperature of the same gas under a second set of conditions. With volume ratios, we started this the other day. I want to show you one with a limiting reagent. I'm not going to give you one with a limiting reagent because it just adds a whole nother level of difficulty that we really don't need. But this is a good one just to review that concept. We already said that coefficients in a balanced equation not only represent moles, but if those substances are gases, which all of the substances are in the synthesis of ammonia from hydrogen and nitrogen gas, those coefficients represent volume. So for example, you can have liters or mils, it doesn't matter, just be consistent. For every 3 liters of hydrogen gas, it will react with 1 liter of nitrogen gas to generate 2 liters of ammonia vapor. Alternatively, you can do it in mils, so you can set up mole ratios. For example, you can do mole ratio or you can do volume ratio. For every 3 moles of hydrogen gas, you'll generate 2 moles of ammonia, or for every 3 mils of hydrogen gas, if you have an excess of nitrogen, you'll generate 2 mils. So you can use those coefficients as volumes as we talked about the other day. This one's a little tricky-wicky. It says what volume of carbon dioxide gas is formed, so you want to know the volume of this, when you have 4 mils of methane gas reacting with 0.5 mils of oxygen gas to form CO2 and water vapor. Classify that equation for me. Combustion. So that's something else. And as you're starting to see now, you've learned a lot, and it's just a matter of integrating it now. All gases are measured at constant temperature and pressure, and that's important. In order to do a volume ratio, you must initially have constant temperature and pressure. If you have 4 mils of this and half a mil of that, what must be your limiting reagent and why? Without dividing by coefficients and the whole thing. Has to be oxygen. Why? There's less of it stoichiometrically, so that is important. So what you're looking at here is for every 1 mil of this, you need 2 mils of this. Well, if you had 4 mils of this, how many mils of this would you need to react with it? 8. And you're not even close, right? So this oxygen gas has to be the limiting reagent because you're not provided with twice as much of it as you are the methane. So here oxygen is the limiting reagent. And what you want to know is the volume of CO2 that should be generated. So what you're looking at here is if you have half a mil of oxygen gas, and you want to know the volume of CO2, keep it in mils, it's easier. From the balanced chemical equation, you can see that you have 2 mils of oxygen gas for every 1 mil of CO2 that you generate, correct? So what's a half times a half? Okay? It's a quarter, right? Half times a half is a quarter. So you can go from the volume of one gas to another if the temperature and pressure are constant. And that'll be the first step in the series of problems we're looking at. So this is a volume ratio, and now we're going to link this to the combined gas law. And this one I think the kids struggle with a little bit more. So we're going to look at 2 examples with the stoichiometry link, and then we'll wrap up the chapter and I'll direct you to the classwork you can do. It says you have 3 liters of methane. Methane is CH4, and some of the kids are like, well, how do you know that? Well, when you look at that balanced equation, what else could methane be? Right? I guess so. So you have 3 liters of methane reacting with oxygen gas at 20 degrees Celsius and 2 atmospheres of pressure. Here's where you have to recognize the key. It says what volume of hydrogen should be generated, it says what volume of water should be generated at 70 degrees Celsius and 3 atmospheres of pressure. Guys, you guys need to take some cough medicine. What you want to recognize, you're given information about methane. You're given the volume of methane under one set of conditions. You want to know the volume of water under a different set of conditions. So is this straight up combined gas law? No, because you have 2 different gases, and that's the key. And that's what I can't really emphasize enough, is reading critically so you can see the key words so you know what to do when. So in this particular problem, you're given information about one gas and you want to find out about the other gas. And this is where you have to be very, very careful. So what you're looking at here, and I like to set up little tables so I can follow along with what the question is giving. So what I've got here is first they're talking about methane. And they said that the volume for methane is 3 liters. The temperature is 20 degrees Celsius or 293.15 Kelvin. And the pressure is 2 atmospheres. Then they're talking about water. They want to know the volume of it. The temperature is 343.15 Kelvin, and the pressure is 3 atmospheres. So at first glance, you're like, ooh, ideal gas law. Let me just smash it in and I'm done. No. You have 2 different gases, Chris, right? 2 different gases. So if you have 2 different gases, you have to be very, very careful. You first have to get the volume of water under the first set of temperature pressure conditions. Once you have that volume, then you'll be able to use the ideal gas law. So this will represent the second set of conditions. This will represent the first set of conditions, but not for water. So the first thing we're going to do in step 1 is do the stoichiometry in regard to volume ratio. And that will allow us to convert from the volume of methane to the volume of water under the first set of conditions. This is just a volume ratio, very, very straightforward from the balanced equation. If they don't give you an equation, which I didn't in the next problem, then you need to write one and balance it. So here you have 1 liter of methane and you will generate 2 liters of water. So for the 1-to-2 volume ratio, and again, this is a volume ratio as we mentioned the other day, 2 times 3 means under the first set of conditions, you have 6 liters of water. That's my V1. And once I get that, I usually will put a line through this so I don't do all this work and forget to use this as V1. Chris?
I thought you could only do volume ratio if it the conditions were the same.
Well, that's what I'm saying. You're going to do this volume ratio at this temperature and this pressure. We're not going to look at this yet. We are going to find V2, but we never knew V1 for the water. We knew what volume was for the methane. So from the volume of methane, I can get the volume of water, and that will be V1 under this first set of temperature pressure conditions. Once I have the V1 for water, then I can go after this missing piece here, V2, because initially I didn't have the volume of water under the first set of conditions. Now I do, and so in step 2 now, what I can do is I can use the combined gas law and I'm going to calculate V2. Because now I have everything for water. So here I've got P1 V1 over T1 is equal to P2 V2 over T2. And now I want to solve V2. So T2 is going there and P2 is going here. And some of you are struggling with variable manipulation. This is an Algebra 1 concept. So if you need more help with it, I'd be happy to help you. But it's not the chemistry, it's the math. So V2 is equal to T2, and now you have everything labeled, so it should all fall into place. The P1 is 2 atmospheres. Be careful with the V1. That's what you got from here. And a lot of kids will do that, and then they won't use it, and that makes a mess. Be careful. Your P2 is 3 atmospheres, and your T1 is 293.15 Kelvin. The Kelvin cancel, the atmosphere cancels. You're left in a volume unit, which is a good sign. And again, in your calculator, you have more than one variable in the denominator, or more than one quantity now. So you're going to need those red parentheses, or you can multiply that off first and flip it. Whatever rocks your world is fine. And that's going to be 4.68 liters. So you need to really be careful with the wording in these problems. You're going to be given information about 2 different gases. You need to find the volume of the gas that you ultimately want to know under the first set of conditions using volume ratio. Once you have that V1, then you can put it through the combined gas law to go after the V2. So it's a multi-step problem. Be very careful. It is easy to make an error. I've got another problem for you to do. I can help you set it up and you can do it. Or if you want, you can just try it, or I'll do it with you. Whatever you want is what we're going to do. But I can't emphasize enough the importance of finishing up classwork 3.2b and not the night before the quiz. This quiz will be hard for many of you. Be careful. You want to do two together, or you want to try and work it? You're going to try and work it? I want to point out one thing to you. I'm asking ultimately about the volume of water at STP. I told you what STP was here, but I don't have to tell you what STP is. You should know. So be very careful there. You need to know what STP is, and it's all over your classwork. So if you've done your classwork, then you know what it is. And if you haven't, then you're really going to be begging for, insight in regard to the quiz. So be careful there. All right. Some hints on number 2. Write down the variables, write out a balanced equation, and let it rip. I'll do it as well. Go. It's propene. Propene is an alkene. It's got a double bond in it. Propane is C3H8. That's like the propane tanks with your where you barbecue from, your grills. But propene has 2 less hydrogen.
What is it used for?
I don't know. We can look that up. Well, I will say this. When I say it, I don't know what you would use it for in everyday life, but if you had propene and you react it with hydrogen gas, you could generate more propane. So I can give you that as a quickie answer, but other than that, I wouldn't be sure. What are you laughing at?
The way you say propane. She's 5.
Just wait till you get to AP Chemistry and we talk about colorimetry, and you talk about why, for example, yellow and blue make green and how your kids learn it. It's kind of funny. It's more PP jokes. Blue and yellow make green. It doesn't make blello.
I think it does. I agree.
All right, let's go. Are you done?
No.
What?
Then stop yakking.
Just like yellow and red make shit.
Make what?
Guys, do your work. Shh. Gotta concentrate. Some of you are going to have trouble balancing this. You can't balance it?
I think I got it.
Da-da-da.
I did that!
There you go.
I did that. I didn't do it right.
Yeah, so go back to that happy method, remember? Oh, no! I'll give you an easy one to balance on the test.
Thank you. That's not gonna be easy.
I don't lie. You should never lie.
Yeah, but it's easy to do it, easy to answer.
That's true.
top it up for like number 3.
That's not nice.
Wait, can you show the calculation?
You have the right balanced equation? I'm not done yet.
How many liters is it?
That's a 6H2O.
Okay. 0.6002.
So the volume ratio is 6.
Yeah, like the change V1. That's balanced.
Wait, how many?
You have V1 what?
Wait, I sort of, that's all we were talking about.
No, you can do the whole thing in mils. Guys, you only need liters for the ideal gas law. Otherwise, if the mils cancel, let it rip.
Oh. Well, I still didn't do it right.
How do you know?
Because I got 0.6666 milliliters of water.
Right, because your conversion was Casa. Should have gotten 6 mils of water initially, right? Just go from 2 mils, use the volume ratio, and 2 times 3 is? No, not.
Oh, yeah.
She just said she don't. I know 70 up. I just don't.
In the middle benchmark part, you get 6 milliliters of H2O. Now we need
Oh, the answer is like how many it is.
No.
Dr. Kayla.
I'm trying to finish. Hang on. No, that's not what we're going to do, but then I'll ask you what you got.
I think I got it. I don't know if I got it though. That was a little too easy.
Guys, it's okay to make a mistake.
But if I got it right, I'll be excited.
Katie, what'd you get?
It's 8 point something.
8.68?
That's what I
That's what
got.
I got.
But don't just copy.
Yeah, the movie.
We literally.
That was way too easy.
Wow, I think it's good geometry.
Guys, really watch your stepwise stuff here. Shh. Come on. Gotta focus. Shh. In the first step, you're going to do the volume ratio. Then you're going to use that volume in the combined gas law. And I know I sound like a broken record. Got to do the classwork to bring it home.
I'm working on it.
That's okay. I almost made a mistake. You know how we found 6 milliliters of water? I almost put a 2 in that.
All right, but do you see the volume ratio here? So just be very meticulous with it. You caught yourself, so it's good. Can't emphasize enough the importance of practice problems. If you do them, you'll be golden. Golden, golden. Questions here? I would try and do a problem before I left today, and if you really want to make sure you're understanding, you'll have this done by tomorrow. Tomorrow we will write up Lab 3-2, and if you have any issues here, we can address them. You want your quiz Monday or Tuesday? Tuesday. So on Monday, for period 5 only, we'll do Lab 3-3. We'll quiz on Tuesday, and then we'll continue to write up the lab. Your test is scheduled. I don't know, I gotta look.
No, Tuesday's RFSA.
Oh yeah, Tuesday is our FSA.
Oh.
Here by then.
Okay, hang on a sec.
No, fifth is
Guys, yeah, but there are a few issues there. Hold on, and we'll discuss that.
I can't have it Monday.
Guys, in regard to stoichiometry with the ideal gas law and the combined gas law, you should be starting to make the linkages. And you can see that while gas laws are for gases only, you can tie them back into solids or liquids through stoichiometry. This finishes our unit on gases, and our unit on gases is extensive. Quiz 3-4 covers the combined gas law, Dalton's law of partial pressure, effusion and diffusion, ideal gas law, as well as the link with stoichiometry in terms of what we talked about today. You've got to make these linkages to be successful in this gas unit.